So our topic for today is about virtual memory. A while ago, in our chapter 7, lesson 8, we introduced the concept of paging and segmentation and analyzed their shortcomings. We now move to discussion of virtual memory. An analysis of this topic is complicated by the fact that memory management is a complex interrelationship between processor hardware and operating system software. We focus first on the hardware aspect of virtual memory, looking at the use of paging, segmentation, and combined paging and segmentation at the same time. Then we look at the issues involved in the design of virtual memory facility in operating system. So in this lesson, this will be our learning objectives. Comparing single paging and simple segmentation, on the other hand, on the one hand, with fixed and dynamic partitioning on the other, we see the foundation for a fundamental breakthrough in memory management. Two characteristics of paging and segmentation are the keys to this breakthrough. Of course, all memory reference within a process are logical addresses that are all memory references within a process are logical addresses that are dynamically translated into physical addresses at runtime. This means that a process may be swapped in and out of memory such that it occupies different regions of main memory at different times during the courses of execution. Number two, a process may be broken up into a number of pieces, and these pieces need not be continuously located in main memory during execution. The combination of dynamic runtime address, translation, and the use of a page or segment table permits this. So this will be the virtual memory terminology. There are two implications. The second more startling than the first, and both lead to improved system utilizations. More processes may be maintained in main memory because we are only going to load some of the pieces of any particular process. There is room for more processes. This leads to more efficient utilization of the processor because it is more likely that at least one or more numerous processes will be in ready state at any particular time. A process may be larger than all of the main memory. One of the most fundamental restrictions in programming is lifted. Without the scheme, we had been discussing, a programmer must be acutely aware of how much memory is available. If the program being written is too large, the programmers must devise ways to structure the program into pieces that can be loaded separately in some sort of overlay strategy. With virtual memory, based on paging or segmentation, that job is left to the OS and the hardware. As far as the programmer is concerned, he or she is dealing with a huge memory. The size associated with this storage, the OS automatically load pieces of the process into main memory as required. So, because a process executes only in main memory, that memory is referred to as real memory. But a programmer or user perceive a potential much larger memory, that which is allocated on this. This latter is referred to as a virtual memory. Again, virtual memory allows for very effective multiprogramming and relieves the user of the unnecessarily tight constraint of the main memory. And this table 8.2 summarizes characteristic of paging and segmentations with or without the use of virtual memory. Locality and virtual memory. The benefits of virtual memory are attractive, but is the scheme practical? At one time, there was considerable debate on this point, but experience with numerous operating systems has demonstrated beyond doubt that virtual memory does work. Accordingly, virtual memory based on either paging or paging plus segmentation has become an essential component of contemporary operating system. And to understand the key issue and why virtual memory was a matter of much debate, let us examine again the task of the OS with respect to virtual memory. Consider a large process consisting of a long program plus a number of arrays of data. Over any short period of time, execution may be confirmed to a small section of the program and access to perhaps only one or two arrays of data. If this is so, then it would be clearly be wasteful to load in dozens of pieces for the process when only a few pieces will be used before the program is suspended and swap out. We can make better use of memory by loading in just a few pieces. Then if the program branches to an instruction or references a data item on a piece not in main memory, a fault is triggered. This tells the OS to bring in the desired piece. Thus, at any one time, only a few pieces of any given process are in memory, and therefore more processes can be maintained in memory. Furthermore, time is saved because unused pieces are not swapped in and out of memory. However, the OS must be clever about how it manages this scheme. In this steady state, practically all of the main memory will be occupied with process pieces so that the processor and OS have direct access to as many processes as possible. Thus, when the OS brings one piece in, it must throw another out. If it throws out a piece just before it is used, then it will just have to go get that piece again almost immediately. Too much of this leads to a condition known as trashing. The system spends most of its time swapping pieces rather than executing instruction. The reasoning is based on the belief of principle of locality, which was introduced during our introduction chapter. To summarize, the principle of locality states that program and data references within a process tend to cluster. Hence, the assumptions that only a few pieces of a process will be needed over a short period of time is valid. Also, it should be possible to make intelligent guesses about which pieces of a process will be needed in the near future, which avoid trashing. And one way to confirm the principle of locality is to look at the performance of processes in a virtual memory environment. This figure is rather famous diagram that dramatically illustrates the principle of locality. We need to take note that during the lifetime of the process, references are confined to a subset of pages. Thus, we see that the principle of locality suggests that a virtual memory scheme may work. For virtual memory to be practically effective, two ingredients are needed. First, there must be hardware support for the paging and or segmentation scheme to be employed. And second, the OS must include software for managing the movement of pages and or segments between secondary memory and main memory. So in this section, we examine the hardware aspect and look at the necessary control structure which are created and maintained by the OS but are used by the memory management hardware. An examination of the OS issues is provided in our next discussion. The term virtual memory is usually associated with systems that employ paging. Although virtual memory based on segmentation is also used and it is discussed, the use of paging to achieve virtual memory was first reported for the Atlas computer and soon came into widespread commercial use. A simple paging, we indicated that each process has its own page table, and when all of its pages are loaded into main memory, the page table for a process is created and loaded into a main memory. Each page table entry contains the frame number of the corresponding page in the main memory. A page table is also needed for a virtual scheme based on paging. Again, it is typical to associate a unique page table with each process. In this case, however, the page table entries become more complex, as shown here in figure 8.2a, paging only. because only some of the pages of the process may be in main memory. A bit is needed in each page table entry to indicate whether the corresponding page is present in main memory or not. If the bit indicates that the page is in memory, then the entry also includes the frame number of that page. The page table entry includes a modified bit indicating whether the content of the corresponding page had been altered since the page was last loaded into main memory. If there has been no change, then it is not necessary to write the page out when it comes time to replace the page in the frame that it currently occupies. Other control bits may also be present. Let's say, for example, if protection of or sharing is managed at the page level, then bits for that purpose will be required. The page table structure. The basic mechanism for reading a word from memory involves the translation of a virtual or logical address consisting of page number and offset into a physical address consisting of frame number and offset using a page table. Because the page table is of variable length depending on the size of the process, we cannot expect to hold it in the registers. Instead, it must be in the main memory to be accessed. In this figure, it suggests a hardware implementation when a particular process is running. A register holds the starting address of the page table for that process. The page number of a virtual address is used to index the table and look up the corresponding frame number. This is combined with the offset portion of the virtual address to produce the desired real address. Typically, the page number field is longer than the frame number field and greater than M. This figure shows an example of a two-level scheme typical for use with a 32-bit address. If we assume byte level addressing the 4K byte 2 raised to 12 pages, then the 4 gigabyte 2 raised to 32 virtual address space is composed of 2 raised to 20 pages. If each of these pages is mapped by a 4-byte page table entry, we can create a user page table composed of 2 raised to 20 PTS requiring 4 megabytes 2 raised to 22. This huge user page table occupying 2 raised to 10 pages can be kept in virtual memory and mapped by a root page table with 2 raised to 10 PTS occurrence occupying 4K bytes 2 raised to 12 of the main memory. In this figure, it shows the steps involved in address translation of this scheme. The root page always remain in main memory. The first 10 bits of a virtual address are used to index into the root page to find a PTE for a page of the user page table. If that page is not in main memory, a page fault occurs. If that page is in main memory, the next 10 bits of the virtual address index into the user PTE page to find the PTE for the page that is referenced by the virtual address. So inverted page table. A drawback of the type of page tables that we have been discussing is that their size is proportional to that of the virtual address space. An alternative approach to the use of one or multiple level page table is the use of an inverted page table structure. Variation on this approach are used on the PowerPC, UltraSpark, and the IA64 architecture. An implementation of the Mac operating system on the RTPC also uses this technique. Typically, the hashing technique results in chains that are typically short between 1 and 2 entries. The page table structure is called inverted because it indexes the table in entries by frame number rather than virtual page number. For a physical memory size of 2 raised to m frames, the inverted page table contains 2 raised to m entries so that the ith entry refers to frame I. Each entry in the page table includes the following. First, the page number. the process identifier, the control bits, and the chain pointer. In this example, the virtual address include an n-bit page number with n greater than m. The hash functions maps the n-bit page number into an m-bit quantity, which is used to index into the inverted page table. Translation look side buffer. In principle, every virtual memory reference can cause two physical memory addresses and accesses, one to fetch the appropriate page table entry and one to fetch the desired data. Thus, a straightforward virtual memory scheme would have the effect of doubling the memory access time. To overcome this problem, most virtual memory schemes make use of a special high-speed cache for page table entries, usually called a translation look-aside buffer. And this cache function is the same way as a memory cache and contains those page table entries that have been most recently used. The organization of the resulting paging hardware is illustrated here, no? In 8.7. Given the virtual address, the processor will first examine the TLB. If the desired page table entry is represented, then the frame number is retrieved and the real address is formed. If the desired page table entry is not found, then the processor uses the page number to index the process page table and examine the corresponding page table entry. The processor also updates the TLB to include this new page and table entry. And finally, if the present bit is not set, then the desired page is not in the main memory and the memory access fault called a page fault is issued. At this point, we leave the realm of hardware and invoke the OS, which load the needed page and updates the page table. This flowchart shows the use of the TLB. The flowchart shows that if the desired page is not in main memory, a page fault interrupt causes the page fault handling routine to be invoked. To keep the flowchart simple, the fact that the OS may dispatch another process while this input-output is underway is not shown. By the principle of locality, most virtual memory references will be to locations in recently used pages. Therefore, most references will invoke page table entries in the cache. There are a number of additional details concerning the actual organizations of the TLB. Because the TLB contains only some of the entries in a full page table, and we cannot simply index into the TLB based on the page number. Instead, each entry in the TLB must include the page number as well as the complete page table entry. The processor is equipped with hardware that allows it to interrogate simultaneously a number of TLB entries to determine if there is a match on the page number. And this technique is referred to as associative mapping. And it is contrasted with the direct mapping or indexing used for lookup in the page here in our next figure. The design of the TLB also must consider the way in which entries are organized in the TLB and which entry to replace when a new entry is brought in. This issue must be considered in any hardware cache design. And this topic is not pursued here. The reader may consult a treatment of cache design for further details. And finally, the virtual memory mechanism must interact with the cache system and this will be illustrated here in this figure. A virtual address will generally be in the form of page number offset, and first the memory system consulted the TLB to see if the matching page table entry is present. If it is, the real or physical address is generated by combining the frame number with the offset. If not, the entry is accessed from a page table once the real address is generated, which is in the form of tag, and the remainder that cache is consulted to see if the block containing that word is present. An important hardware design decision in the size of page to be used. There are several factors to consider. One is internal fragmentation. Clearly, the smaller the page size, the lesser is the amount of internal fragmentations. To optimize the use of main memory, we would like to reduce internal fragmentation. On the other hand, the smaller the page, the greater is the number of pages required per process. More pages per process means larger page table. For large program is a heavily multi-program environment, and this may mean that some portions of the page tables of active process must be in virtual memory, not in main memory. Thus, there may be a double page fault for a single reference to memory. First, to bring in the needed portion of the page table, and second, to bring in the process page. Another factor is that the physical characteristic of most secondary memory devices, which are rotational, favor a larger page size of more efficient block transfer of data. Complicating this matter is the effect of page size on the rate at which page faults occurs. This behavior in general terms is defective in this figure and is based on the principle of locality. If the page size is very small, then ordinarily a relatively large number of pages will be available in the main memory for a process. After a time, the pages in memory will all contain portions of the process near recent references. Thus, the page fault rate should be low. As the size of the page is increased, each individual page will contain location farther and farther from any particular recent reference. Thus, the effect of the principle of locality is weakened and the page fault rate begins to rise. Eventually, however, the page fault will begin to fall as the size of the page approaches the size of the entire process. When a single page encompasses the entire process, there will be no page faults. A further complications is that the page fault rate is also determined by the number of frames allocated in a process. In this number of page frames allocated shows that for a fixed page size, the fault rates drops as the number of pages maintained in a main memory grows. Thus, a software policy interacts with the hardware design decisions. This table lists the page sizes used on some machines. Finally, the design issue of page size is related to the size of physical main memory and program size. At the same time that main memory is getting larger, the address space used by the application is also growing. The trend is most obvious on personal computers and workstation, where applications are becoming increasingly complex, and furthermore, contemporary programming techniques used in a large program tend to decrease the locality of references within a process. So segmentation, the virtual memory implication. In segmentation allows the programmer to view memory as consisting of multiple address space or segments. Segments may be of unequal, indeed dynamic size. Memory references consist of a segment number offset from of address. And this organization has a number of advantages to the programmer over a non-segmented address space, as written here. Organization. In the discussion of simple segmentation, we indicated that each process has its own segment table, and when all of its segments are located into main memory, the segment table for a process is created and loaded in the main memory. Each segment table entry contains the starting address of the corresponding segments in main memory, as well as the length of the segment. The same device, a segment table, is needed when consider a virtual memory scheme based on segmentations. Again, it is typical to associate a unique segment table with each process. In this case, however, the segment table entries become more complex. As what we have here, because only some of the segments of the process may be in the main memory. A bit is needed in each segment table entry to indicate whether the corresponding segment is present in main memory or not. If the bit indicates that the segment is in memory, then the entry also includes the starting address and length of that segment. Now, both paging and segmentation have their strengths. Paging, which is transparent to the programmer, eliminates external fragmentation and thus provides efficient use of main memory. In addition, because the pieces that are moved in and out of main memory are of fixed equal size, it is possible to develop sophisticated memory management algorithm that exploit the behavior of programs as well as we shall see. Segmentation, which is visible to the programmer, has the strength listed earlier, including the ability to handle growing data structure, modularity and support for sharing and protection, and to combine the advantages of both. Some systems are equipped with processor hardware and OS software to provide both. In a combined paging or segmentation process, a user's address space is broken up into a number of segments at the discretion of the programmers. Each segment is in turn broken up into the number of fixed size pages, which are equal in the length to a main memory frame. If a segment has length less than that of a page, the segment occupies just one page. From the programmer's point of view, a logical address will consist of a segment number and a segment offset. From the system's point of view, the segment offset is viewed as a page number and page offset for a page within the specified segment. So in this figure, it suggests a structure to support combined paging segmentation. Associated with each process is a segment table and a number of page tables, one per process segment. When a particular process is running, a register holds the starting address of the segment table for that process. Presented with a virtual address, the processor uses the segment number portion to index into the process segment table to find the page table for that segment. Then the page number portion of the virtual address is used to index the page table and look up the corresponding frame number. This is combined with the offset portion of the virtual address to produce the desired real address. Protection and sharing. Segmentation lends itself to the implementation of protection and sharing policies because its segment tables entry includes a length as well as a base address. A program cannot inadvertently access a main memory location beyond the limits of a segment. To achieve sharing, it is possible for a segment to be referenced in the segment tables of more than one process. The same mechanism are of course available in a paging system. However, in this case, the page structure of programs and data is not visible to the programmer, making the specification of protection and sharing requirements more awkward. In this figure, it illustrates the types of protection relationship that can be enforced in such systems. More sophisticated mechanism can also be provided. A common scheme is used to ring protection structure of type. In this scheme, lower numbered or inner rings enjoy greater privilege than higher numbered or outer rings. Typically, ring 0 is reserved for kernel functions of the OS with applications at a higher level. Some utilities or OS services may occupy an intermediate ring. Basic principle of the ring systems are as a program may access only data that reside on the same ring or a less privileged ring. A program may call services residing on the same or a more privileged ring. The operating system software. The design of the memory management portion of an OS depends on the three fundamental areas of choice. Number one, whether or not to use virtual memory techniques. Number two, the use of paging or segmentation or both. And number three, the algorithm employed for various aspects of memory management. As we shall see here, the task of memory management in paging environment is fiendishly complex. Furthermore, the performance of a particular set of policies depends on main memory size, the relative speed of main and secondary memory, the size of the number of processes competing for resources, and the execution behavior of individual programs. This latter characteristic depends on the nature of the applications, the programming language that compiler employed, the style of the programmer who wrote it, and for an interactive program, the dynamic behavior for the user. Thus, the reader must expect no final answer here or anywhere. For a smaller system, the OS designer should attempt to choose a set of policies that seems good over a wide range of conditions based on the current state of knowledge. For larger system, particularly mainframes, the operating system should be equipped with monitoring and control tools that allows the site manager to tune the operating system to get good results based on site conditions. The page policy. The page policy determines when a page should be brought into main memory. The two common alternatives are demand paging and pre-paging. With demand paging, a page is brought into main memory only when a reference is made to location on that page. If the other elements of memory management policy are good, the following should happen. When a process is first started, there will be a flurry of page faults. As more and more pages are brought in, the principle of locality suggests the most future references will be to pages that have recently been brought in. Thus, after a time, matters should settle down and the number of page faults should drop to a very low level. With pre-paging, pages other than the one demanded by a page fault are brought in. Pre-paging exploit the characteristic of most secondary memory devices such as this, which have seek times and rotational latency. If the pages of the process are stored contiguously in secondary memory, then it is more efficient to bring in the number of contiguous pages at one time rather than bridging them in one at a time over an extended period. Of course, this policy is ineffective if most of the extra pages that are brought in are not referred. The pre-paging policy could be employed either when a process first startups, in which case the programmer would somehow have to designate desired pages, or every time a page fault occurs. This latter course would seem preferable because it is invisible to the programmer. However, the utility of pre-paging has not been established. Pre-paging should not be confused with swapping. When a process swaps out of memory and put in a suspended state, all of its resident pages are moved out. When the process is resumed, all of the pages that were previously in main memory are returned to main memory. The placement policy. It determines where a real memory, a process species is to reside. In a pure segmentation system, the placement policy is an important design issue. Policies such as best fit, first fit, and so on, which are possible alternatives. However, for us systems that uses either pure paging or paging combined with segmentation, placement is usually irrelevant because the address translation hardware and the main memory access hardware can perform their functions for any page frame combination with equal efficiency. Replacement policy. In most operating systems, the treatment of memory management include a section entitled Replacement Policy, which deals with the selection of a page in main memory to be replaced when a new page must be brought in. And this topic is sometimes difficult to explain because several interrelated concepts are involved. We shall refer the first to concept of precedence set management, which is dealt with in next subsection, and reserve the term replacement policy for the third concept, which is discussed in the subsection. Frame locking. One restricted on replacement policy needs to be mentioned before looking at various algorithms. Some of the frames in main memory may be locked. When a frame is locked, the page currently stored in that frame may not be replaced. Much of the kernel of the OS, as well as key control structures, are held in locked frames. In addition, I/O buffers and other time-critical areas may be locked into main memory frames. Locking is achieved by associating a lock bit with each frame, and this bit may be kept in the frame table as well as being included in the current page table. The basic algorithms. Regardless of the resident set management strategy, there are certain basic algorithms that use for the selection of a page to replace. Replacement algorithms that had been discussed in the literature include optimal, least recently used, first in, first out, and clock. So the optimal policy selects for replacement that page for which the time to the next reference is the longest. It can be shown that this policy results in the fewest number of page faults. Clearly, this policy is impossible to implement because it would require the OS to have perfect knowledge of the future events. However, it does serve as a standard against which to judge real-world algorithms. In this figure, it gives an example of an optimal policy. The example assumes a fixed frame allocations for this process of 3 frames. The executions and of the process requires reference to 5 distinct pages. The page address stream formed by executing the program is 3 or 232152 4532 and 52, which means that the first page reference is 2, the second page reference is 3, and so on. The optimal policy produces 3 pages faults after the frame allocation has been filled. The least recently used policy replaced the page in the memory that has not been referenced for the longest time. By the principle of locality, this should be the page less likely to be referenced in the near future. And in fact, the least recently used policy does not nearly as well as the optimal policy. The problem with this approach is the difficulty in implementation, and what one approach to be tagged each page with the time of its last reference. This would have to be done at each memory reference, both instruction and data. So even if the hardware would support such a scheme, the overhead would be tremendous. Alternatively, one could maintain a stack of page reference, again an expensive prospect. In this figure, it also shows an example of a behavior of LRU using the same page address stream as the optimal policy example. And there are 4 page faults, as I mentioned a while ago: the first in, first out, the clock policy. Actually, this figure provides an example of a simple clock policy mechanism. A circular buffer of n main memory frames is available for page replacement. Just prior to the replacement of a page from the buffer with incoming page 727, the next frame pointer points at a frame 2 which contains page 45. The clock policy is now executed because the use bit for 45 in the frame 2 is equal to 1. This page is not replaced. Instead, the use bit is set to 0 and pointer advances. The behavior of the clock policy is illustrated here. The presence of an asterisk indicates that the corresponding use bit is equal to 1, and the arrow indicates the current composition of the pointer. We need to take note that the clock policy is adept at protecting frames 2 and 5 from replacement. In this figure, it shows the result of an experiment reported in which compared the 4 algorithms that we have been discussing earlier. It is assumed that the number of page frames assigned to the process is fixed, and the results are based on the execution of 0.25 times 10 raised to 6 references in Fortran program using a page size of 256 words. In summary, the page replacement algorithm cycles through all of the pages in the buffer looking for one that has not been modified since being brought in and out. has not been accessed recently. Such a page is a good bet for replacement and has that advantage that because it is unmodified, it does not need to be written back out to secondary memory. If no candidate page is found in the first sweep, the algorithm cycles through the buffer again looking for a modified page that has not been accessed recently. Even though such a page must be written out to the replace because of the principle of locality, it may not be needed again anytime soon. If the second pass fails, all of the frames in the buffer are marked as having not been accessed recently, and third sweep is performed. The strategy was used on the earlier version of the Macintosh virtual memory scheme, as illustrated here in our 8.18 figure. The advantages of the algorithm over the simple clock algorithm is that pages that are unchanged are given the preference for replacement because a page that has been modified must be written out before being replaced. There is an immediate saving of time. So page buffering, although LRU and the clock policies are superior to FIFO, they both involve complexity and overhead not suffer with FIFO. In addition, there is a related issue that the cost of replacing a page that has been modified is greater than for one that has not, because the former must be written back out to second memory. Replacement policy in cache size. Main memory size is getting larger and the locality of application is decreasing. In compensation, cache sizes have been increasing. Large cache size, even multi-megabyte ones, are now feasible design alternatives. With a large cache, the replacement of virtual memory pages can have a performance impact. If the page frame selected for replacement is the cache, then the cache block is lost as well as the page that it holds. Resident set management. The resident set size with page virtual memory, it is not necessarily and indeed may not be possible to bring all of these pages of a process into main memory to prepare it for execution. The OS must decide how many pages to bring in, that is how much main memory to allocate to a particular process. With these factors in mind, two sorts of policies are to be found in contemporary operating system. A fixed allocation policy gives our process a fixed number of frames in main memory within which to execute. That number is decided at initial load time and may be determined based on the type of process or may be based on guidance from the programmer or system manager. With fixed allocation policy, whenever a page fault occurs in the execution of a process, one of the pages of that process must be replaced by the needed page. The variable allocation policy allows the number of page frames allocated to a process to be carried over the lifetime of the process. Ideally, a process that is suffering persistently high levels of page faults, indicating that the principle of locality only holds in a weak form for the process, will be given additional page frames to reduce the page fault rate, whereas a process with an exceptionally low page fault rate, indicating that the process is quite well behaved from a locality point of view, will be given a reduced allocation with the hope that this will not noticeably increase the page fault rate. The use of the variable allocation policy relates to the concept of replacement scope as explained in the next subsections. The variable allocation policy would appear to be more powerful one. However, the difficulty with the approach is that it requires the OS to assess the behavior of active processes, and this inevitably requires software overhead in the OS, and it is dependent on hardware mechanism provided by the processor platform. Replacement scope. The scope of a replacement strategy can be categorized as global or local. Both types of policies are activated by a page fault when there are no pre-page frames. A local replacement policy chooses only among the resident pages of the process that generated the page fault in selecting a page to replace. On the other hand, a global replacement policy considers all unlocked pages in main memory as candidates for replacement, regardless of which process owns a particular page. Well, it happens the local policies are easier to analyze, and there is no convincing evidence that they perform better than a global policy, which are attractive because of their simplicity of implementation and minimal overhead. There is a correlation between replacement scope and resident set size. A fixed resident set implies a local replacement policy is to hold the size of a resident set fixed. A page that is removed from main memory must be replaced by another page from the same process. A variable allocation policy can clearly employ a global replacement policy. The replacement of a page from one process is main memory with that of another causes that allocation of one process to grow by one page and that of the other to shrink by one page. We shall also see that variable allocations and local replacement is a valid combination, and we can examine these three combinations. So in the fixed allocation local scope, for this case, we have a process that is running in the main memory with a fixed number of frames. When a page fault occurs, the OS must choose which page from along the currently resident pages for this process is to be replaced. Replacement algorithms such as those discussed in the preceding subsection can be used. With a fixed allocation policy, it is necessary to decide ahead of time the amount of allocation to give to a process. This could be decided on the basis of the type, the application, and the amount requested by the program. The drawback to this approach is twofold. If allocation tend to be too small, then there will be a high page fault rate, causing the entire multi-programming system to run slowly. If allocation tend to be unnecessarily large, then there will be too few programs in main memory, and there will be either considerable process idle time or considerable time spent in swapping. So variable allocation and global scope. This combination is perhaps the easiest to implement and has been adopted in a number of operating systems. At any given time, there are a number of processes in main memory, each with a certain number of frames allocated to it. Typically, the OS also maintains a list of free frames. When a page fault occurs, a free frame is added to the resident set of a process and the page is brought in. Thus, a process experiencing page faults will gradually grow in size, which should help reduce over all page faults in the system. One way to counter the potential performance problem of a variable allocation global scope policy is to use page buffering. In this way, the choice of which page to replace becomes less significant because the page may be reclaimed if it is referenced before the next time that a block of page are overwritten. For the variable allocation or local scope, the variable allocation or local scope strategy attempts to overcome the problem with a global scope strategy, and it can be summarized here. So with this strategy, the decision to increase or decrease a resident set size is a deliberate one. It is based on the assessment of the likely future demands of active processes. Because of this evaluation, such as a strategy is more complex than a simple global replacement policy. However, it may yield better performance. The key elements of the variable allocation local scope strategy are criteria used to determine resident set size and the timing of changes. One specific strategy that has received much attention in the literature is known as working set strategy. Although a true working set strategy would be difficult to implement, it is useful to examine it as a baseline for comparison. Okay, so the virtual time is defined as follows. So consider the sequence of memory frequencies, in which R sub I is the page that contains the ith virtual address generated by a given process. So in this figure, it is illustrated actually in this figure, which shows a sequence of page reference for the process. The dots indicated time units in which the working set does not change. We need to take note that the larger the window size, the larger is the working set. And this can be expressed in the following relationship. So This strategy is appealing because it takes an accepted principle, the principle of locality, and exploit it to achieve a memory management strategy that should minimize page faults. And that the past does not always predict the future, but the size and the membership of the working set will change over time. At demand cleaning, or the cleaning policy. A cleaning policy is the opposite of the fetch policy. It is concerned with determining when a modified page should be written out to secondary memory. Two common alternatives are demand cleaning and pre-cleaning. With demand cleaning, a page is written out to secondary memory only when it has been selected for replacement. A pre-cleaning policy writes modified page before their page frames are needed, so that page can be written out in the batches. There is a danger in following either policy to the full. With pre-cleaning, a page is written out but remains in main memory until the page replacement algorithm dictates that it be removed. Pre-cleaning allows the writing of pages in batches, but it makes little sense to write out hundreds or thousands of pages only to find that the majority of them had been modified again before they are replaced. The transfer capacity of secondary memory is limited and should not be wasted with unnecessary cleaning operations. On the other hand, with demand cleaning, the writing of a dirty page is coupled to and precedes the reading in of a new page. This technique may minimize page writes, but it means that a process that suffers a page fault may have to wait for two-page transfer before it can be unblocked. This may decrease processor utilization. A better approach incorporates page buffering and disallow the adoption of the following policy. Clean only pages that are replaceable but decouple the place on two lists, modified and unmodified. The pages on the modified list can periodically be written out in the batches and moved to be an unmodified list. A page on the unmodified list is either reclaimed if it is referenced or lost when its frame is assigned to another page. The load control is concerned with determining the number of processes that will be resident in main memory, which has been referred to as the multi-programming level. The load control policy is critical in the effective memory management. If too few processes are resident at any one time, then there will be many occasions when all processes are blocked and much time will be spent in swapping. On the other hand, if too many processes are resident, then on average, the size of the resident set of each process will be inadequate and frequent faulting will occur. The result is thrashing. Thrashing, as is illustrated here in 8.21, as the multi-programming level increases from a small value, one would expect to see processor utilization rise because there is a less chance that all resident processes are blocked. However, a point is reached at which the average resident set the inadequate. At this point, the number of page fault rises dramatically and processor utilization collapses. So I have here the process suspensions. If the degree of multi-programming is to be reduced, one or more of the currently resident process must be suspended. Here is the list of 6 possibilities. Lowest priority process, faulting, last process activated, process with the smallest resident set, largest process, and process with the largest remaining execution window. So as in so many other areas of OS design, which policy to choose is matter of judgment and depend on any other design factors in the OS as well as the characteristics of the program being executed. Because Unix is intended to be machine independent, its memory management scheme will vary from one system to the next. In SB R4 in Solaris, there are actually 2 separate memory management schemes. The paging system provides a virtual memory capability that allocates the page frame in main memory to processes and also allocates the page frames to these block buffers. Although this is an effective memory management scheme for user process and disk I/O, a page virtual memory scheme is less suited to managing the memory allocations for the kernel. For this latter purpose, a kernel memory allocated is used, and we examine two mechanisms in turn. The paging system. And we have here the Unix SB4 memory management parameters. Actually, most of the fields defined in this table are self-explanatory. The type of storage field in the disk block descriptor is needed for the following reason. When an executable file is first used to create a new process, only a portion of the program and data for the file may be loaded into the real memory. Later, as page faults occur, new portions of the program and data are loaded. It is only at the time of first loading that virtual memory pages are created and assigned to locations on one of the devices to be used or for swapping. At the time the OS is told whether it needs to clear C to 0, the location in the page frame before the first loading of a block of the program or data. So, page replacement. The page frame data table is used for page replacement, and several pointers are used to create lists within this table. All of the available frames are linked together in the list pre-frames available for bringing in pages. When the number of available frames drops below a certain threshold, the kernel will steal a number of frame to compensate. And this will be the two this will be the page table, this block descriptor, page frame data table, and swap use table. The two parameters determine the operations of the algorithm, and this is the scan rate and hand spread. The parameter varies linearly between the values slow scan and fast scan, as the amount of free memory varies between the values lost free and main free. In other words, as the amount of free memory shrink, the clock hands move more rapidly to free up more pages. The hand spread parameter determines the gap between the front hand and the back hand. And therefore, together with scan rate, determines the window of opportunity to use a page before it is the swap out due to lack of use. So this will be the kernel memory allocator. Most of these blocks are significantly smaller than the typical machine page size, and therefore the paging mechanism would be inefficient for dynamic kernel memory allocations. The Linux memory management. Linux share many of the characteristics of the memory management schemes of other Unix implementation, but has its own unique features. Overall, the Linux memory management scheme is quite complex. So Linux virtual memory. So Linux makes use of a 3-level page table structure consisting of the following types of table as what we have here. To enhance the efficiency of reading in and writing out pages to and from main memory, Linux defined a mechanism for dealing with contiguous blocks of page map into contiguous block of page frames. For this purpose, the body system is used, and the kernel maintains a list of contiguous page frame group the fixed size. A group may consist 1, 2, 4, 8, 16, 32 page frames. As pages are located and delocated in the main memory, the available groups are split and merged using the body algorithm. The page replacement algorithm, the Linux page replacement algorithm is based on the clock algorithm described in our example earlier. No? In the simple clock algorithm, a use bit and modify bit are associated with each page in main memory. In the Linux scheme, the use bit is replaced with an 8-bit age variable. Each time that a page is accessed, the age variable is incremented. In the background, Linux periodically sweeps through the global page pool and decrements the age variable for each page as it rotates through all the pages in the main memory. A page with an age of 0 is an old page that has not been referenced in some time, and is the best candidate for replacement. The larger the value of the age, the more frequently a page has been used in recent times, and the less eligible it is for replacement. Thus, the Linux algorithm is form of at least frequently used policy. The Linux kernel memory capabilities manage physical main memory page frames. Its primary function is to allocate and deallocate frames for a particular user. Possible owners of a frame include user space processes, dynamically allocated kernel data, static kernel code, and the page cache. The Windows memory management. The Windows Virtual Memory Manager controls how memory is allocated and how paging is performed. The Memory Manager is designed to operate over a variety of platforms and to use page sizes ranging from 4 kilobytes to 64 kilobytes. Intel and AMD 64 platforms have 4 kilobytes per page, and Intel Titanium platform have 8 kilobytes per page. So here is the 32-bit platform. Each Windows user process at a separate 32-bit address space, allowing 4 gigabytes of virtual memory per process. This will be the Windows paging. When a process is created, it can, in principle, make use of entire user space of almost 2 gigabytes. This space is divided into fixed size pages, any of which can be brought into main memory, but the OS manage the addressing in a contiguous regions allocated the 64 kilobyte boundaries. A region can be in one of these 3 states: available, reserved, and committed. So a number of design issues relates to OS support for memory management, and that is the pitch policy, placement policy, replacement policy, resident set management, cleaning policy, and load control. And this will be our reference. And that's it for virtual memory. Thank you for listening and good luck, everyone.